Okay, let's take what we learned about quadratic equations and use that to solve some physics. All right, so suppose that Jack is on a faraway planet, standing on top of a cliff. Now, I put Jack on a faraway planet just to make our numbers easier here. This would have to be a certain number if this took place on Earth. But if I put it on some faraway planet, I'm free to make this number whenever I want. So it'll make it work out easier for us. Okay, so Jack is on some faraway planet. He's standing at the top of a cliff, and he's going to jump off this cliff. So obviously he jumps, maybe he jumps up first and then down, but he'll fall and hit the water eventually. All right, so he's on top of a cliff. His height above the water after t seconds, so t represents seconds. So we're going to plug t into this function, plug seconds into the function. So his height above the water after t seconds is given by this equation. So we plug t into this function, and the function spits out his height above the water. So you plug in a time measured in seconds, the function will tell you how high Jack is above the water, measured in feet. All right, so let's answer some questions then. So how high was the cliff? Okay, so let's think about that. How high was the cliff? Well, t represents seconds after Jack jumps. So initially, Jack was standing on top of the cliff. Okay, so if we want to know how high the cliff was, we want to know where Jack was, or his height, at time 0 initially. Okay, so we want to plug 0 in for t. We're wanting to find h of 0. So at time 0, or at 0 seconds after he jumped, that would give us where Jack was standing, which was the top of the cliff, and that'll tell us how high the cliff was. So how high was the cliff? H of 0. If I plug 0 in for t, I'll get 80. I think when you're doing a word problem, you should always include the units. So not just 80, but 80 what? Is it 80 seconds? No, it's not 80 seconds. It's the height. Height is measured in feet. So that would be 80 feet. So the cliff was 80 feet tall. When did Jack reach his maximum height? Okay, so what shape does this graph make? Well, this is a quadratic equation, so it's going to make a parabola. How does it open? Well, the leading coefficient, the a, is negative, so it opens down. Okay, so we have a parabola that opens downward, like this. So his maximum height will occur at the vertex of that parabola. Okay, we want to know when did he reach his maximum height. So we're wanting the t value of the vertex. Okay, how do we find the t value of the vertex? Well, you learned a simple little formula for that. So t will equal negative b over 2a. Those are some ugly b's and a. Let me try that again. Negative b, still pretty ugly, over 2a. All right, so my b is 30. So that'll be negative 30 over 2 times a, which would be negative 5. Negative 30 over negative 10 would be 3. Hey, 3 what? Well, we want to know when that happened. We solve for t. T is measuring in seconds. So make sure we include units and say 3 seconds. Okay, so he reaches his maximum height at 3 seconds. What was his maximum height? Well, if he reaches his maximum height at 3 seconds, and we plug 3 in for t into this function, the function will spit out his height at 3 seconds. So that'll tell us his maximum height at 3 seconds. So we are wanting h of 3. So I'm just going to plug 3 in here. 3 squared is 9. Negative 5 times 9 is negative 45. 30 times 3 is 90, so plus 90, and plus 80. Negative 45 plus 90 is 45. 45 plus 80 is 125. 125 what? Is it seconds? No, it's not seconds. This function spits out feet, so that's 125 feet for his maximum height. All right. When did he hit the water? Okay, so Jack jumps off this cliff. We want to know when he hits the water. All right. What was Jack's height above the water when he hit the water? Well, his height above the water when he hits the water would be 0. This function tells us the height, so we want to know when the function value is equal to 0. So we're wanting to know when 0 is equal to negative 5t squared plus 30t plus 8. So we're wanting to find the roots of this quadratic equation, or the zeros, or the x-intercepts. We should always hunt a GCF first. We have a greatest common factor of 5 here, so let's divide both sides of this equation by negative 5. That will give us 0 equals t squared minus 6t minus 80 divided by 5. So 5 going to 81 times 5 is 5. 30, it's like 16. So minus 16. All right, this will factor. So 0 is equal to, looks like it'll factor into t minus 8 and t plus 2. 2 minus 8 is negative 6. Negative 8 times 2 is negative 16. All right, if you multiply two numbers together and the answer is 0, then either of those could be 0. So either t minus 8 is equal to 0, or t plus 2 is equal to 0. So either t is equal to 8, or t is equal to negative 2. Okay. T represents seconds, so this is 8 seconds, or negative 2 seconds. All right, so we have two solutions here. Let's think about those. Does t equals negative 2 make any sense in this problem? So that would be 2 seconds before Jack jumped. Does this equation apply 2 seconds before Jack jumped? Well, no, because all he's really doing is standing on top of the cliff before he jumped. Or I guess we really don't know what he was doing before he jumped. But he definitely wasn't falling through the air. So this equation doesn't apply before the initial time. So the only one that makes any sense in this problem is t equals 8. Okay, so it took Jack 8 seconds to hit the water after he jumped. All right, let's make a graph of this equation. Notice that we've already found the initial value, the vertex here and here, and the roots. So my roots were at 8 and negative 2. Okay, my vertex was at 3. And 125. And that is one ugly looking parabola. Try to make that a little better. All right, make sure this is symmetrical. I guess I could keep going down this way. All right, so if 3's the axis of symmetry, 5 this way gets me 8, 5 this way gets me negative 2, so that makes sense. All right, let's think about this part. So as we've already talked about, times less than 0 don't make any sense in this problem. Okay, so we need to get rid of this over here. So everything before that doesn't matter. Okay, does this equation apply after Jack hits the water? No, it doesn't. This equation just applies as he's falling through the air. Once he hits the water, the way that he's falling over, his speed changes completely. So this equation doesn't apply when he hits the water. So we don't need any of this equation down this way. So really the only part that's important to us in this problem is this that I have butchered. Okay, so this part of the parabola over here and this part down this way forever is irrelevant to our problem. We're only concerned with this part as he's falling through the air. All right, his initial height was 80 feet, so that's here. So this equation gives his height. So notice he initially started at 80 feet. So he must have jumped up in the air, and he went up to 125 feet at 3 seconds. Jack could really jump. Looks like he jumped 45 feet into the air. Wow. And so he started at 80 feet, he jumped up until his height was 125 feet, and then he began falling again until his height was at 0, 8 seconds after he jumped. All right, let's think about Jack's velocity. So his initial velocity would have been 0 because he was, or before he jumped would have been 0 because he was just standing there. Okay, and then notice that he goes up first. So his velocity was initially positive. He jumped up in the air. Okay. As he's going upward, his velocity is slowing down. So of course gravity's pulling him downward. So he jumps up, his velocity is getting slower and slower and slower until he gets to the top of his jump where his velocity stops. And now then he would start falling, so his velocity would now be negative. So going up, it's positive velocity. Going down, negative velocity. And notice it gets more, he would get faster and faster as he fell, so his velocity would increase more and more and more. All right, question number 6. What was his average velocity over the time interval from 5 to 7? So let's make some room here. So his average velocity over the time interval from 5 to 7. Okay, remember that velocity is the change in position, or in this case, the change in height. So we write the change in height over the change in time. All right. On this graph, we have time on the horizontal axis, height on the vertical axis. So if velocity is the change in height over the change in time, we'd have the change in height over the change in time, or the change in y over the change in x. The change in y over the change in x is just the slope. So what we're really wanting here is the slope of this curve, of this graph. Notice that the slope changes over time. Okay, the slope gets steeper and steeper and steeper as we go down like this. And as we just talked about, the slope measures the velocity. His velocity should be getting faster and faster and faster, more and more negative as he's falling. So the slope should get steeper and steeper and steeper as he's going along in time. So the velocity changes as we move along, but we can find the average velocity over this time interval. Remember, to do that, we need these 2 points, and we're going to find the slope of the secant line through those 2 points. So to find the change in height, we will need to do h of 7 minus h of 5. That'll tell us the change in height. And this will be measured in feet. Over the change in time, that'll be 7 minus 5 seconds. H of 7, so we're going to plug 7 in here. That'll be 49 times negative 5. see, 49 times 5, let's see, 49 times 10 is 490. So 245. Come on. I hope that's right. I better double check that. 49 times 5. 9 times 5 is 520. Yeah, 245. 30 times 7 is 210. Plus 210 plus 80. All right, so negative 245 plus 210 is negative 35 plus 80. 80 minus 35 is 45. Obviously, you can use a calculator to do that arithmetic, and you should probably check what I just did. I might have made a mistake there. All right, minus h of 5. So let's plug 5 into this equation. 5 squared is 25. 25 times 5 is 125. So negative 125. Plug 5 in here. 30 times 5 is 150. Plus 80. 150 minus 125 is 25. 25 plus 80 is 105. And 7 minus 5. That's feet. That's seconds. 45 minus 105 is negative 60. And 7 minus 5 is 2. My units are feet per second. Reduce that just a little bit more, and I get negative 30 feet per second. So the slope of this secant line is negative 30. It should be negative. It's going downhill. The velocity should be negative because Jack is falling, so that makes sense. And everything looks good.